The story of life on Earth has a paradox at its very core, a profound contradiction that challenges everything we think we know about our own origins. For its first few 100 million years, our planet was a hellscape, a boiling sphere of magma under a relentless cosmic bombardment. Yet the moment things calmed down, the second the first oceans formed, life appeared. Not tentatively, but with an explosion of activity, as trillions of microbes conquered every corner of the young world. This is deeply strange. It's as if life was simply waiting in the wings for its cue. Not only did it appear impossibly fast, but in that tiny sliver of time, it crossed a gargantuan gap. To be considered alive, even the simplest microbe must perform a set of complex tasks. It must eat, metabolize, grow, and multiply. To do any of this, it needs a genome, the biological instruction manual for building and operating an organism. How dead chemistry with no instructions became a living thing with instructions is one of the greatest mysteries in all of science. The riddle is a classic chicken and egg problem on a monstrous scale. To build the complex proteins that make a cell work, you need instructions from a genome. But to build and read a genome, you need proteins. It's a closed loop, a fortress of complexity that life somehow had to breach. Starting from a soup of simple, dead molecules and reaching this level of sophistication by pure chance should have taken an astonishing amount of time for trial and error. So how did the first living things do it in just a few 100 million years? Perhaps we are looking at the clock all wrong. Imagine the story of life as a book. As time passed, more and more characters were added to its pages. Amoebae, fish, dinosaurs, and mammals. Over billions of years, the book of life grew thicker, its story more complex. The genome itself is this book, a long string of biological instructions. And from the first microbes to us, the length of this book seems to have grown at a surprisingly constant rate. The functional genome of a fish is more than twice that of a worm. Ours is about twice that of a fish. It's as if evolution has been following an exponential inner clock, doubling the complexity of life on average every 350 million years. But here is where it gets truly strange. The very first microbes on Earth, as simple as they seem, already had long and complex genomes. They were not chapter 1. They were already deep into the story. How could they have achieved that complexity so quickly? There is one fascinating, mind-bending answer. We can take this evolutionary clock and run it backwards. Back past the first microbes on Earth, back to the simplest conceivable life form, a single biological letter. When we do that, the clock doesn't stop at the birth of the Earth. It keeps ticking backwards until it lands 10 billion years in the past. More than twice the age of our world. This means that if life truly evolved this way, its story didn't begin here. It began somewhere else out there in the ancient universe. This would explain everything. Why life appeared so quickly. It wasn't starting from scratch. It was arriving as a mature seed, just waiting for water and warmth to reawaken. And why the first microbes were already so sophisticated. They were the product of billions of years of evolution that happened somewhere else entirely. But could life really be that old? Could it have survived in a universe just born from the Big Bang? Yes. In fact, there was a time when the entire universe may have been a perfect incubator for life. At its most fundamental level, life needs two things: the right chemical elements and a liquid medium, like water, where those elements can interact. Today, we search for this in the tiny Goldilocks zone around stars. But immediately after the Big Bang, the universe itself was unimaginably hot. As it expanded, it cooled. And for a brief window of time, between 10 and 17 million years after the beginning, the ambient temperature of the entire cosmos was between 0 and 100 degrees Celsius. The exact temperature range for liquid water. For a few million years, more than 13.7 billion years ago, you didn't need a planet or a sun to have liquid water. The entire universe, every single inch of it, had the right temperature to support life. Of course, temperature isn't enough. You also need elements like carbon and oxygen, forged in the hearts of stars. But even in these super early cosmic times, the first stars may have already existed. Monstrous, massive suns that lived fast and died young, exploding as supernovae in just a few million years, seeding the baby universe with all the chemical ingredients needed for life. Or perhaps the first life was even more exotic, thriving not in water but in ammonia or ethane, liquids that could have been sustained by the fading warmth of the Big Bang for tens of millions of years longer. The true magic of this idea is its scale. While the universe today is a vast, cold, and deadly vacuum, back then, the conditions for life were everywhere. For millions of years, primordial organisms could have emerged on any suitable rock, even adrift in the space between the stars, sowing the cosmos with the seeds of what would, billions of years later, become bacteria, dinosaurs, and us. Eventually, the universe cooled too much, and this cosmic habitable epoch ended. But life, once started, is tenacious. Some of these ancient life forms may have survived, frozen in asteroids or hibernating as spores in cosmic dust. Tiny seeds roaming the dark for eons, waiting for a new, warm home. If this is true, then life isn't a rare miracle. It's a cosmic inheritance. Of course, this is a speculative story. Both the habitable baby universe and the exponential clock of life are plausible, scientifically grounded ideas, but they are not yet proven. Just one possible answer to the question of our existence. But if life did come to Earth from space, it almost certainly seeded other worlds in our own solar system. We might find fossils of it in the dry riverbeds of Mars. We might find it thriving today in the warm, underground oceans of Enceladus or Europa. Saturn's moon Titan has rivers and lakes of ethane, as warm as the universe was 90 million years after the Big Bang. Finding truly exotic life there would be a monumental discovery. So far, when we look to the stars, we see only silence. But maybe that's because it takes 10 billion years of evolution for a species to become complex enough to build a radio telescope. Perhaps there are millions of worlds filled with microbes, oceans teeming with exotic fish, and continents covered in bizarre animals. And maybe, just maybe, others like us, who have only just awoken to consciousness and are looking up at their own sky, wondering if they are alone. The true story of our origins might be grander and more ancient than we ever imagined, written not on one world, but across the entire cosmos. Exploring these possibilities is at the heart of what we do. To join us on more journeys into the amazing, the terrifying, and the unknown, make sure to subscribe and press the bell so you never miss a new exploration. So, here is a question for you. What idea do you find more profound, that life is a near impossible miracle unique to Earth, or that we are all the descendants of an ancient, universe-spanning Genesis? Share your thoughts in the comments below.